First, I would like to thank the organizers for having me here for this opportunity. I'll be talking about synchronization properties of delay coupled electronic oscillators, specifically the effects of heterogeneity in such oscillators. So the oscillators are all around us, very common around us, whether we talk about circadian rhythms or we talk about neurons or we talk about mechanical oscillators or even we talk about social phenomena such as clapping of large audiences. All right, and these oscillators are not isolated, they talk to each other in some manner and they try to synchronize or they show emergent behavior such as synchronization. And sometimes this talking takes place naturally and sometimes it happens, it so happens that we need these oscillators to talk to each other so that they can perform a particular task. The oscillator I am going to talk about is called phase lock loops. These are electronic oscillators and these oscillators have three components. The first one is the phase detector PD, which collects the signal, and then there is a loop filter which filters out the high frequency component and then it sends it to an autonomous oscillator which is called voltage controlled oscillator or VCO to modulate its frequency. All right, so the equation in this case is given by theta dot k or phi dot k, which is the instantaneous frequency is equals to the intrinsic frequency of this VCO plus this modulation term. All right, so this is the coupling strength and this is the connectivity matrix, and we have three time delays in the system. The first one is this feedback delay for this connection. The second one is the transmission delay from one PLL to another PLL, and there is a third delay which is the processing delay because of the filtering process in this system. Right, and this PU is actually the impulse response function of this loop filter and given by this expression, and it is characterized by the cutoff frequency of the filter or the characteristic time of that filter. Now these PLLs are used in many applications, and in those applications we need these oscillators to be synchronized. And the classical way or the state of the art way for doing that is by forcing them with a master clock which is more precise clock, right? And the way we are going to talk about here is the self-organization case where we connect these oscillators to each other and we try to synchronize them without any external force. All right, and this is inspired by or motivated from the biological oscillators where we said in the last session we talked about these oscillators can synchronize and make patterns, and this is self-organization in the sense there is no external force working on these oscillators and still they manage to synchronize somehow. And and in the last session we also talked about, or in the last session it was talked about that these oscillators and this synchronization happens even if there is a noise in the system and with a lot of heterogeneity because of the natural diversity in these oscillators. All right. So the similar thing happens in electronic oscillators as well, because we have unavoidable irregularities in the production processes which leads to the system level variation in these oscillators, and these variations are not negligible, these are large enough. In fact, in many cases special auxiliary circuits are added to the device to in order to mitigate the effects of this mismatch or heterogeneity. All right, so to study the effects of these heterogeneous oscillators, we take two oscillators to start with, and we take different frequencies, coupling strength, filtering process, different transmission delay and feedback delays. So these are the parameters which can be heterogeneous, and we ask these questions. The first one is, can we achieve stable synchronized state in this system, and can we predict, if we can find such solutions, can we predict the resulting state and control it? As it happens that the set of equation, this integral differential equation, can be actually reduced to a second order Kuromoto model, which is more widely applicable. And in fact, any PLL system with Ath order filter can be reduced to A plus 1th order Kuromoto model. So using these two forms of the system, mathematical forms of this system, we try to analyze the behavior of the system, the effects of heterogeneity, and can we find the synchronized solution. So we start with the synchronized solution, which is when the frequency of both of these oscillators is equal, and maybe there's a constant phase difference between them. And when we look for these solutions, we get a transcendental equation for the frequency, and the expression for phase difference is given by this expression. And in the absence of heterogeneity, what happens is we have exact in phase and antiphase solutions. But in the presence of heterogeneity, because of these terms, what happens is we have a modified in phase solution and a modified antiphase solution. And we can also look at the stability of these solutions by perturbing these solutions a little bit, and then look at the nature of these perturbations, how these perturbations behave. And we get this characteristic equation, and based on whether this the largest eigenvalue, real part of the largest eigenvalue is either 0 or greater than 0 or less than 0, we can say that the solution is stable or unstable or neutrally stable. Now, when we look at these solutions in parameter space, namely with coupling strength and transmission delay, these blue regions represent the places where we have stable modified in phase solutions. And then there are these regions, these are red regions where we have modified antiphase states stable. And of course, the overlapping region is where both of such solutions coexist. And now there are some regions here as well, which are white regions where the solutions exist, but they are unstable. And there are then these green regions where solutions do not exist. All right. So the synchronization solution in these green regions do not exist. And this can be understood from the form of the solution. And of course, because if the value inside this square root is negative, then we don't have any synchronized solution. And the transition from the no synchronization region to a synchronization region, or the region where we have the synchronized solution, takes place via saddle node bifurcation. All right, so before we go to the heterogeneous case, we look at why these instability arise in our system, and the reason is the filtering process. So if we increase the integration time or the characteristic time of the loop filter, or we decrease the cutoff frequency, correspondingly the cutoff frequency of that loop filter, we have more and more unstable regions in our system. And now we ask, can we use heterogeneity to induce synchronization, and can it be helpful, heterogeneity can be helpful for controlling the dynamics via two examples, specifically by looking at the cutoff frequency of the filter and the heterogeneity in the transmission delay. So this is one example, the first example, where we have on x-axis we have the mean cutoff frequency, on the y-axis we have the heterogeneity in this cutoff frequency. As we see at 0, we have this gray region where we do not have any solution. And then if we increase the heterogeneity in the system, heterogeneity in cutoff frequency specifically, then we reach to this green region where we have at least one synchronized solution stable. All right, so by increasing this heterogeneity, we are actually restabilizing the synchronized solution in our system. And we can look at the same thing here in this animation, where this branch is getting stabilized as we increase the heterogeneity in this cutoff frequency. All right, the second part is, can we use it to somehow control our dynamics? And the answer lies here in this solutions. If we look at these solutions, simplified form of these solutions, we can say that the heterogeneity in the delay, which is delta tau, and beta are linearly dependent. All right. So beta is the phase difference or phase, it will give you the phase configuration between these PLLs. And on the other hand, there is no dependency of heterogeneity on omega. That means it only depends on the mean value. So this means that if we keep the mean value of the transmission delay same and increase the heterogeneity, we do not change the value of the omega, that is the collective frequency or the synchronized frequency or the stability of that frequency, but we can change the phase configuration of the system. And this is what we can do here in this case. So these are the two solutions. So we can get any phase configuration by just changing or tuning the delay heterogeneity in the system, because it's a linearly dependent. So if we want any value, it will not change the value or the stability of that solution, but we can change the phase configuration by tuning. Any phase configuration can be obtained by tuning delay heterogeneity. And this happens with other parameters as well. So we managed to verify our results in experimental setup as well. So this is the prototype device where the results are quite well matching. For example, in this case, we start in this experiment, we start with two different frequencies for the homogeneous system, and then in the middle of this experiment, what we do is we tune our cutoff frequency to two different values, keeping the mean value constant, and we get to a single frequency solution, that is the synchronized solution with a constant phase difference as well, which is near zero in this case. All right, so the key observations are there are different types of heterogeneities in our system. Frequency mismatch or heterogeneous transmission delay, filtering process, heterogeneity in filtering process, feedback delay, and of course there is coupling strength, which will influence all of these factors as well in some way. But the important point in this case is that with increasing heterogeneity, we can actually restabilize the synchronized solution, and heterogeneity can be helpful for finding out or tuning a particular, finding out a particular phase solution or phase configuration in our system. And these results have been summarized in these two publications, and thank you for your kind attention.
Thank you for being in time. So we have good time for questions. Yes, Puneet?
You can hear me, right?
Yeah.
This was very reminiscent of Potter's work, right? What is the difference that what he had done?
Can you please repeat?
Alison Motter, the guy was supposed to come here.
Oh, okay.
As well.
So yeah, there's a difference between this work and that one. So in that work, they actually get a new solution because of the heterogeneity. And in this case, we have already unstable solutions which are getting stabilized because of the many factors, which is, for example, the delay and the periodic nature of the coupling function and so on. So the new solutions and unstable solutions getting restabilized.
Okay, I have one question, Nirmal. So you have taken this cosine
Function.
this coupling. So is it usual for your electronic circuit or?
No, it's actually that phase loop or PD, phase detector, which we talked about, that is the first component of our system, is like a multiplier. So if you have a sinusoidal signal,
that makes the synchronized solution unstable because cosine of.
No, it just shifts a little bit.
I see.
It's not unstable, but it shifts a little bit. So if you have a sinusoidal function, you will have in phase solution, then anti-phase solution, then in phase solution. For cosine, it happens like the first one is anti-phase and then in phase. So it's a pi/2 shift.
Pi/2 shift. Okay. So if we don't have any further question, let us thank Nirmal for a very nice talk.
Thank you.